Welcome to this explainer. Right now, as you're listening to this, you have billions of perfectly engineered, microscopic machines inside your body that are literally keeping you alive. Today, we're setting off on a really incredible architectural journey. We're taking a deep dive into the absolute fundamental building blocks of life, proteins. We're going to explore exactly how these wildly intricate microscopic structures are built from the atomic level all the way up. And, maybe more importantly, we're going to learn how great doctors actually use this precise molecular architecture to understand, diagnose, and treat diseases on a full-scale clinical level.
Now, if there is literally just one thing you take away from our entire time together today, let it be this golden rule of medical biochemistry. Structure dictates function. Period. A protein's biological activity is entirely determined by its specific three-dimensional conformation, which we call its native state. This shape is absolutely everything. If you alter that shape, the protein loses its function, and it's that specific loss of function that leads directly to human pathology.
So here's our roadmap for this micro to macro journey. We'll start by looking at how structure dictates biological function. Then we'll break down the hierarchy of protein folding. From there, we'll compare structural scaffolds to molecular machines, examine the severe pathology of misfolding, look at enzymes as biological catalysts, and finally discover how proteins act as diagnostic tools in a clinical setting.
Okay, part 1. Structure dictates biological function. Let's dive right into this first crucial concept, the central dogma of medical biochemistry. Like we just mentioned, the native state is everything. But what actually happens when that delicate, highly specific state gets disrupted? Well, the protein denatures. Things like extreme changes in temperature, shifts in pH, or genetic mutations can completely destroy a protein's native state. But why does that happen? Think about it. If you apply extreme heat, you're massively increasing the kinetic energy of the molecule. You are quite literally shaking the delicate internal bonds apart. If you change the pH, you alter the electrical charge of the amino acids, which just shatters the ionic bonds holding the whole structure together. When the shape is physically altered or unraveled, the function is gone. And this isn't just some abstract chemistry concept. This is the fundamental molecular basis of human disease. Basically, when proteins break down, the body breaks down. Moving on to part 2, the hierarchy of protein folding. To truly understand how these diseases happen, we really have to visualize proteins being built from the ground up.
Nature methodically builds a protein in 4 distinct steps. It's a lot like laying the foundation and framing a house. Step 1 is the primary structure. This is just a linear sequence of amino acids linked together by incredibly strong covalent peptide bonds. Step 2 is the secondary structure, where this linear chain starts to fold into local geometric patterns. We're talking rigid, rod-like alpha helices or flat beta-pleated sheets, and these are held together by hydrogen bonds. Step 3 is the tertiary structure, which is the full, complex 3D fold of a single chain. The unique R groups on each amino acid dictate this final shape, which in turn completely dictates how the protein interacts with its environment. And finally, step 4 is the quaternary structure. Now, this only happens when multiple individually folded chains lock together to form a larger complex. It's a brilliant level of organization because it allows for complex, dynamic regulation of the protein rather than just making it bigger.
You know, the immense power of that step 1 primary sequence really can't be overstated. It contains absolutely all the information necessary for the protein to fold correctly into its final highly complex 3D shape. If you have a single genetic typo, literally just one point mutation in that linear sequence, the entire structure can fail catastrophically. A classic example is a very specific mutation where a hydrophilic, water-loving amino acid called glutamic acid is accidentally replaced by a hydrophobic, water-fearing amino acid called valine. Because valine hates water, it panics and tries to hide, causing the entire hemoglobin protein to physically clump together with other hemoglobin molecules. Sickle cell anemia is the ultimate clinical proof of this. One wrong amino acid completely alters the hemoglobin protein, causing red blood cells to deform into a sickle shape and leading to severe systemic disease. So the real question is how that 3D shape actually stays together once it's finally folded. The tertiary structure is driven by specific R group interactions. First, you have the hydrophobic effect, where nonpolar groups literally hide away from water by burying themselves deep in the center of the protein. Then you have salt bridges, which are electrical, ionic bonds between acidic and basic groups. And you also have disulfide bridges, which are incredibly strong covalent bonds between specific cysteine residues. Actually, fun fact, those strong disulfide bridges are exactly what get broken and chemically reformed when you go to a salon to get a perm to curl your hair. They're nature's structural staples, and they are absolutely crucial for the stability of extracellular proteins, like insulin, that have to float out in the harsh environment of the blood.
All right, let's hit part 3, scaffolds versus molecular machines.
Once these specific folds are built, they generally fall into two distinct functional categories.
We can pretty cleanly divide proteins into the tough builders and the active workers. On one side, we have fibrous proteins. These are elongated, rope-like, and highly water-insoluble because they purposefully expose their hydrophobic amino acids so they can interlock into really tough fibers. They provide the structural scaffolding and protection for our bodies. Think collagen in your tendons or keratin in your hair and skin. On the flip side, we have globular proteins. These are water-soluble, compact, and spherical because they carefully tuck their hydrophobic amino acids safely inside. They are the highly active molecular tools doing the chemical heavy lifting in your fluids, like hemoglobin carrying oxygen through the blood or enzymes driving active chemical reactions.
Now, let's look at what happens when that fibrous scaffolding fails. Let's look specifically at collagen, the most abundant protein in the entire human body. Collagen relies on a unique, tightly wound triple helix structure to give it incredible tensile strength. But here's a fascinating clinical pearl. Vitamin C is a required cofactor for the specific enzyme that modifies the amino acid proline, which is what allows this massive helix to lock together in the first place. Without vitamin C, the triple helix literally destabilizes and falls apart. This biochemical failure causes scurvy, leading to severe skin sores and bleeding gums. This is exactly why British sailors, historically nicknamed limeys, carried massive stockpiles of citrus on long ocean voyages. They literally needed vitamin C to prevent their structural scaffolding from dissolving. Alternatively, if there's a genetic mutation in the collagen itself, it leads to osteogenesis imperfecta, commonly known as brittle bone disease.
And hemoglobin brilliantly illustrates the other side of the coin, dynamic globular proteins. Hemoglobin is the absolute master of transport because it doesn't just hold a static shape, it physically shifts its conformation to adapt to its environment. It exists in two primary states. The T state, or tense state, has a very low affinity for oxygen. This is perfect for when it's traveling through your deep tissues and needs to unload oxygen to your hungry cells. But in the lungs, it shifts into the R state, or relaxed state, which has a wildly high affinity for oxygen, favoring rapid loading. This shift is driven by a really cool mechanism called positive cooperativity. The very first oxygen molecule struggles to bind, but once it finally does, it physically pulls on the protein structure, ripping open the other binding sites so the next three oxygen molecules snap in easily. It's a highly evolved, dynamic, breathing molecular machine.
Which brings us to part 4, the pathology of misfolding. What happens when this intricate, highly specific folding process goes catastrophically wrong?
Well, when proteins fail to fold correctly, they don't always just sit there uselessly. They can actually become actively toxic to the body. In a condition called amyloidosis, misfolded proteins clump together into insoluble beta sheet aggregates called amyloid fibers. These fibers crush surrounding cells, and this exact process is a primary hallmark of Alzheimer's disease. But even scarier are prion diseases. Prions are terrifying because they contain absolutely no DNA or RNA. They are literally just rogue, misfolded protein shapes. Yet, they act like infectious zombies. When a prion bumps into a completely normal healthy protein in the brain, it forces that healthy protein to misfold on contact. This chain reaction leads to rapid, fatal neurodegeneration, like in Creutzfeldt-Jakob disease. And because they're just tightly folded proteins rather than living bacteria or viruses, standard hospital sterilization often can't even destroy them. Wild, right?
Okay, let's jump to part 5, enzymes as biological catalysts. Shifting gears a bit, let's explore the most dynamic, fast-paced subset of globular proteins.
These are the biological catalysts responsible for almost every single chemical reaction currently keeping you alive. But to understand enzymes, you have to understand activation energy. Think of it like a massive, steep hill you have to push a heavy boulder over before it can roll down the other side. Enzymes do not change your starting point at the bottom of the hill or your ending point on the other side. The overall equilibrium of the reaction stays exactly the same. Instead, enzymes effectively lower the hill. They do this at a specific 3D pocket called the active site. Now, this isn't just a static lock and key. Through an induced fit, the enzyme binds the substrate and dynamically undergoes a physical conformation change. It acts like a microscopic vice, bending and straining the chemical bonds of the target to its absolute breaking point, making that leap over the energy barrier dramatically easier and millions of times faster.
The mathematical language we use to describe this incredible efficiency is called Michaelis-Menten kinetics. Imagine a graph tracking the speed of an enzyme. As you add more substrate, the speed shoots up, but eventually it levels off at a hard ceiling. That absolute top speed ceiling is Vmax, the maximum velocity when the enzyme is completely saturated and working as fast as physically possible. Now find exactly half that maximum height on your mental graph and look straight down at the required substrate amount on the x-axis. That amount right there is your Km. What you absolutely need to remember is that Km is an inverse measure of affinity. A very low Km means the enzyme is incredibly sensitive. It has a wildly high affinity for its target and works brilliantly, snapping up its target instantly, even when there is barely any substrate floating around.
And this mathematical relationship brilliantly illustrates how modern pharmacology actually works in your body. We design life-saving drugs to exploit these exact mechanics by inhibiting overactive enzymes. In competitive inhibition, a drug directly fights the natural substrate to physically sit in the active site. Because they're competing for the exact same parking spot, the apparent Km increases, meaning the enzyme's affinity drops. But if you flood the system with enough natural substrate, you can overcome the drug and still reach the exact same Vmax. A perfect real-world example of this is statins, which compete with molecules in your body to block cholesterol production. In non-competitive inhibition, however, the drug doesn't fight for the active site at all. Instead, it binds to a biochemical backdoor on the enzyme called an allosteric site. This physically warps the entire active site from the outside in, effectively breaking the machine. Because the active site is warped, the maximum speed, or Vmax, plummets regardless of how much substrate you add.
And finally, part 6, proteins as diagnostic tools. Let's move to our last macro-level topic to see how this all comes together clinically.
We've seen how proteins function on a microscopic level. Now let's see how great doctors use them as diagnostic tools. When a physician suspects an inflammatory disease or a blood cancer, they can order a serum protein electrophoresis, or SPEP. By running an electrical current through a sample of blood serum, we physically separate the floating proteins by their electrical charge and their size into 5 distinct fractions. This gives us a literal window into the patient's internal organs without making a single incision. For example, a massive decrease in the albumin fraction might signal severe liver cirrhosis because the damaged liver just stops producing it. A drop in alpha-1 globulin points straight to early-onset emphysema. The beta fraction carries our LDL cholesterol, and the gamma fraction contains our body's vital immune antibodies.
And speaking of that gamma region, take a look at the M spike. This is a sudden, sharp, narrow peak shooting up in the gamma region of an electrophoretic graph. When a doctor sees this distinct shape, immediate clinical alarm bells go off. Because the gamma region houses our antibodies, an incredibly concentrated, narrow spike there represents a massive, uncontrolled overproduction of a single, cloned type of antibody. It tells the physician immediately that the patient likely has multiple myeloma, which is a dangerous type of blood cancer originating in the plasma cells.
Beyond electrophoresis, we also have highly specific, gold-standard diagnostic biomarkers. Remember, these specialized proteins belong safely inside their designated cells to do their jobs. Therefore, finding them floating freely in the blood tells a stark story of cellular destruction. If a doctor draws your blood and finds troponin floating in it, it means your cardiac muscle cells have literally ruptured and spilled their internal contents into your bloodstream. It is the definitive, undeniable proof of a heart attack or myocardial infarction. C-reactive protein, or CRP, acts as a systemic flare gun, signaling massive, acute inflammation occurring somewhere in the body. And creatine kinase, specifically the CKMB fraction, acts as a highly reliable marker of severe muscle damage.
So we wrap up our architectural journey with this question. How does the microscopic folding of a single molecule completely dictate your macroscopic health? From the single genetic typo that causes sickle cell anemia, to the missing vitamin that unravels our structural scaffolding, all the way to the terrifying misfolded prions that destroy the brain, it all comes back to our golden rule. Structure dictates function. By deeply understanding this incredibly precise microscopic architecture, we unlock the profound ability to diagnose, treat, and ultimately understand the complex machinery of human life. Keep marveling at the microscopic world around you, and thanks for joining me on this explainer.